Hello everyone and welcome to a new chapter where we'll be discussing how to process data in parallel. Over the last decade, the big data movement has exploded. We now collect a huge amount of data about pretty much everything. The weather, the financial markets, and for better or worse, data about the users of our applications. The current challenge for software engineers is to make sense of all that data in a reasonable amount of time. Ironically, this increased demand for processing power comes at a time when CPU speed is no longer growing year on year at the same pace it once did. The solution found by the industry is to add more CPU cores to each computer. And when this is not enough, distribute the processing task across a fleet of computers. However, this paradigm shift hasn't been easy. We can't take a program meant to run on a single thread and expect it to work seamlessly across several processors. Why is that? Well, the short explanation is that in a concurrent environment, it's extremely difficult to work with shared, mutable data. Either it leads to race conditions, meaning that some threads can access a program in an inconsistent state, resulting in some very tricky bugs. Or we get deadlocks where nothing gets done, because all threads are waiting on each other. While it is theoretically possible to avoid these issues, it's notoriously difficult in practice. I recently watched an interview with Mozilla's Jim Blandy, co-author of Programming Rust. In the interview, Jim mentioned that an engineer at Mozilla decided to use a thread sanitizer tool to look for data races in their C++ codebase. And he found that in every case where Firefox used threads, there were data races. Not just in some or most cases, but every single case. Those bugs were eventually fixed, but how many companies actually take such a precaution? The problem gets even worse if we plan to distribute the program across nodes in a data center. In that case, we have to worry about how to send the data across the network and how to retry in case of hardware failures. Processing big data is an extremely complicated topic. And that's why many frameworks such as MapReduce, Spark, or Flink were developed to cater for this use case. It's also interesting to note that most of the ideas these frameworks are based on have their roots in functional programming patterns. How is that? Well, the most common answer is that in functional programming, we use immutable data structures. So if we can't change the data, then it's safe to share it between threads or computers. And that's it. It's a bit like this meme about how to draw an owl, where in step 1 you draw 2 circles, and in step 2 you draw the rest of the owl. It's not wrong, but the biggest part of the explanation is missing. So the goal for this chapter is to fill this gap, and we'll do so by implementing a parallel collection from scratch. Then, we'll use this data structure to analyze a real-world dataset of average temperature by cities. This is much a bigger project than in the previous chapters, which is great because it will give us time to apply all the functional design techniques in a realistic scenario. We will also learn new features about Scala and its standard library, such as for loops, recursions, enumerations, and futures. Are you excited? I certainly am. So I'll see you soon for the next lecture. Bye.